I'd like to welcome everybody to today's presentation on the interaction of hormones and neurotransmitters. I am your host, Dr. Dawn-Elise Snipes. We're going to get a general understanding of the most important hormones and neurotransmitters in behavioral health. And I'm going to go through a lot of these things. What I really want you to just kind of get a global understanding of is how many different neurotransmitters are involved in things like mood and energy and even gut motility and things like that. So we can't just say, well, if you have a low mood, it must be serotonin. Oh, no. It could be a whole bunch of other things. And so we're going to look at how all those things go together. But first, let's review what the neurotransmitters do and talk a little bit about how they interact with other things. So serotonin is a neurotransmitter with 7 families, 5-HT1 through 5-HT7, and approximately 15 different receptor subtypes. So there are a lot of different ways that serotonin affects the body and affects the brain. And it's important to recognize that because certain antidepressants, certain serotonin reuptake inhibitors will act on some serotonin receptors, but not other types. And Buspar, for example, buspirone, acts on certain serotonin receptors, but not others. And so it's important to recognize what receptors do what if you are a psychiatrist, if you're a prescribing person. All we need to know is that serotonin is basically involved in everything: mood, energy and glutamate release, respiration, blood pressure, appetite, pain perception. As serotonin goes down, our pain threshold goes down as well. Bone density, memory, learning and cognition, motivation and dopamine release. So serotonin and dopamine are really closely linked. Acetylcholine, dopamine, and norepinephrine release in the frontal cortex. Remember, that's where we have all of our executive functioning, our decision making, and our impulse control and our motivation stuff. And GI motility. About 90% of serotonin is actually stored in the gut as opposed to in the brain, which is kind of an interesting little fact there. Serotonin is among the many neurotransmitters that participate in the regulation of cortisol, prolactin, and growth hormone secretion. Remember that cortisol is your main stress hormone. So serotonin kind of helps try to regulate cortisol levels. When we have low dopamine, when we have low serotonin, we can have low dopamine. Low dopamine means low prolactin. Prolactin is a hormone that we're not even going to talk about today that regulates behavior, the immune system, metabolism, reproductive systems. It decreases estrogen and testosterone and is high during times of stress. So we can see that, if serotonin is low, we already can see that if serotonin's low, then it's likely dopamine is going to be low. So we're going to start having problems because dopamine does a lot with motivation and energy, among other things. Now, I created these 2 mnemonics to help me remember each one of them in order. And they're not in any particular order except for in order to make the mnemonic. Snagged E are your neurotransmitters, and that stands for serotonin, norepinephrine, acetylcholine, glutamate, GABA, endorphins, dopamine, and your endocannabinoids. CAT-T-DOPE stands for cortisol, adrenaline, thyroid hormones, testosterone, DHEA, oxytocin, progesterone, and estrogen. Now, you'll see on the infographic that's in your classroom, as well as on each of these slides, if it is purple, that means as the target neurotransmitter or chemical goes up, that other one goes down. So as serotonin goes up, norepinephrine goes down. As serotonin goes up, acetylcholine goes down. As serotonin goes up, glutamate goes down. Serotonin is one of our calming neurotransmitters, so you would expect that because norepinephrine, acetylcholine, and glutamate are excitatory. GABA is made from glutamate, but it also goes up in in relation to serotonin, because GABA is one of our relaxation neurochemicals. So when we feel happy, when we feel relaxed, then GABA is also going to go up. Endorphins, our endogenous opioids, also go up. These are our pleasure chemicals. These are the things that are released or involved in addiction. When people take an addictive substance or engage in an addictive behavior, there's a rush of dopamine. And when dopamine goes up for pleasure, then endorphins also go up. So as serotonin goes up, endorphins go up. Likely, dopamine goes up. In your emotion processing areas of your brain, there is a positive correlation between serotonin and dopamine. So that's one of those things that we just kind of want to remember. Interestingly, though, in the prefrontal cortex, that area that's responsible for executive functioning, if there is an imbalance between dopamine and serotonin, if dopamine is low and serotonin is high, people tend to be much more aggressive. So we want to look for not only neurotransmitters, but also where these things are taking place. And your endocannabinoids, your natural cannabis-like chemicals, work with serotonin to help modulate the HPA axis. They help downregulate it when it's time to downregulate it. In terms of hormones, when serotonin goes up, cortisol and adrenaline and testosterone all go down. We want to take down the excitatory things. Now, you'll see in a couple of places, I have some hormones that are both colors. And that means that in response to the target chemical, in this case serotonin, estrogen sometimes goes up and sometimes goes down. What we want to know about estrogen is that it's excitatory, and too much estrogen tends to cause anxiety, but it can also be somewhat neuroprotective. So there are some areas where estrogen does go up. DHEA is one of those hormones that we have that a lot of people talk about in terms of aging. It's one that goes down as we age, and it is associated with helping us have energy and good mood. Oxytocin's our bonding chemical. When we feel more relaxed, when we feel happier, we tend to want to bond with others more. And progesterone, interestingly enough, in most cases has anti-anxiety effects. So just like serotonin tends to help us deal with anxiety, when it's certain serotonin receptors do, when it's at the right level, progesterone also helps us deal with anxiety. Now, serotonin's interesting because when the 5-HT2 receptors are targeted, they actually are excitatory, and too much of that kind of serotonin or too much of those excitement of those receptors can actually cause anxiety. So we have this little balance that you're going to start to see. And then obviously serotonin here is crossed out because serotonin doesn't impact itself. Now, norepinephrine is the next one we're going to talk about. Norepinephrine is a excitatory neurochemical. It is produced from phenylalanine, which is an amino acid. Phenylalanine is broken down to tyrosine, which is another amino acid. You can get tyrosine from your diet. It's really easy. Tyrosine, now this is a really interesting scenario here. Tyrosine is broken down to make L-DOPA, and L-DOPA is converted to dopamine. Okay, well, that's great. But did you know that epinephrine is made from dopamine and norepinephrine is made from epinephrine? So let's just follow this backwards. If a person has a crappy diet and they're not getting enough tyrosine, then there's a really good chance that their dopamine, epinephrine, and norepinephrine levels are all low. So they're probably going to experience some fatigue, some difficulty concentrating, and some low motivation. Now, it could be a breakdown somewhere else in the system, but we always want to consider with neurotransmitters, I'm going to have to take my glasses off because they are dirty as all get out. We always want to consider with neurotransmitters that the problem can be caused by the person not having enough raw materials to make that neurotransmitter. So you might not have enough to begin with. It might be caused by a breakdown in the creating the precursors for some reason. There's a breakdown in that system. It might be that there is a problem in the signaling to get, for example, norepinephrine released into the synapse. That system may not be working, so norepinephrine may not be released like it's supposed to. Norepinephrine may not stay in the synapse for long enough because it is either absorbed too quickly or the components that act to break down norepinephrine and decompose it, actually there's too many of those. Or on the far end of this whole system, even if norepinephrine stays in the synapse for long enough and it connects to those receptors on the other end in order to transmit the signal, if that system is broken, if the signal is not transmitting effectively, then there can be a problem. So knowing exactly what's causing the imbalance is not easy. And right now it's a lot of art and a little bit of science, because we can't, like I've told you before, there is no blood test, for example, that can measure the effectiveness of the neurons and the neuronal systems in our brain. And there's no blood test that can measure the levels of neurotransmitters in our brain. So we have to look and try to figure out what's going on. Norepinephrine regulates circadian rhythms, is responsible for attention and focus, assists with heart rate and blood pressure regulation. Remember, it comes from epinephrine, which is another word for epinephrine is adrenaline. You can also call them adrenaline and noradrenaline, whatever you want to call them. It's an excitatory neurotransmitter, and it's going to ramp things up. It regulates the release of glucose and fatty acids into the blood. Norepinephrine is the one that's telling the organs to release the energy so we can fight or flee. Too much norepinephrine can cause panic. It also modulates the immune response, suppresses neuroinflammation when released in the brain. So that's really important too. It not only does it excite things, but it also helps suppress inflammation. It helps buffer against that neurotoxicity. Another interesting fact is that up to 70% of norepinephrine projecting cells are lost in people with Alzheimer's disease, which is one of the reasons they have difficulty with attention and focus. But remember that norepinephrine is responsible for so much more. So their circadian rhythms and even their blood pressure and their regulation of their blood glucose may start going wonky when norepinephrine is out of balance because the projecting cells are lost. What does norepinephrine interact with? And I'm going to go through a lot of these very quickly because we're going to talk about it more in depth at the end. But I just wanted you to get an idea even from just looking at it. Remember, as norepinephrine goes up, the things that are purple go down, and the things that are orange go up. So as norepinephrine goes up, serotonin and acetylcholine goes down. And acetylcholine also reduces serotonin, which is an interesting concept. Glutamate goes up, GABA goes down, thyroid and testosterone go down, progesterone tends to go down, and that's partly because in the presence of HPA axis stimulation, in the presence of cortisol, we will see progesterone is broken down to make cortisol. So progesterone is initially secreted, but it doesn't go all the way through the system because it's broken down early in order to make cortisol. And we know that when the HPA axis is activated, cortisol is secreted, norepinephrine and adrenaline are all secreted. So those are some interesting things to look at. And I want you to think about your clients as we go through this. not only the ones that, present with mood disorders, but let's think about what other physiological issues they may be having. If they've got hypothyroid or low testosterone or low estrogen levels, how is that impacting all of these other neurotransmitters? And so as norepinephrine goes up, testosterone goes down. If people have low testosterone, it's likely they may have high levels of norepinephrine. Now, acetylcholine is involved in muscle control, arousal, attention, memory, and motivation. These are a lot of the same things that dopamine is also involved in. So that's interesting to kind of note that acetylcholine and dopamine do a lot of similar things. Acetylcholine is excitatory. In the absence of glutamate, or when there's glutamate resistance, remember we've talked about glucocorticoid resistance in other classes. When the person is too stressed for too long, the receptor cells become resistant to that glutamate, so they don't react the way they're supposed to. Well, when that happens, or if enough glutamate just isn't there, then acetylcholine becomes the primary excitatory neurotransmitter. We know that acetylcholine and serotonin tend to have an inverse relationship. So if somebody has high levels of acetylcholine, we can guess that their serotonin levels are probably going to be low. The interesting thing is that acetylcholine also reduces norepinephrine, and that is not something that I expected to find, because generally norepinephrine goes along with glutamate and adrenaline in the HPA axis response. GABA, dopamine, and your endocannabinoids, those feel-good chemicals tend to go down when acetylcholine goes up. But your endorphins, your inner opioids, your endogenous opioids go up. Why is this? Well, generally under stress, part of the activation of the HPA axis increases the level of endorphins when it's operating functionally in order to help us not feel pain during that fight or flee process. Now, this kind of gets out of whack, it goes wonky, if the person's HPA axis is dysregulated or chronically activated. Then the body may start developing endorphin resistance as well. So when acetylcholine goes up, there is a good chance that HPA axis has been activated, and cortisol, adrenaline, thyroid hormones, testosterone, DHEA, and estrogen may go up in certain areas of the body. Now, I say certain areas. You see how this can all get a little bit complicated? Because our libido under stress tends to go down. So you're like, well, why in the heck are testosterone and estrogen going up? Well, because certain testosterone and estrogen receptors are responsible for helping us have energy and helping us with that fight or flee. So it depends on where in the body the receptors are getting activated. And it's also important to remember that under excessive chronic stress, when we start seeing glucocorticoid resistance, when we start seeing endorphin resistance, we also may start seeing thyroid resistance or thyroxine resistance. So we may, and lower levels of thyroid stimulating hormone. So we may have somebody who's presenting with symptoms of hypothyroid as a result of chronic stress. Glutamate is your main excitatory neurotransmitter. This is almost a worse bad guy than cortisol in many ways because it can actually excite cells to their death. It can ramp up the heat so much, ramp up the energy so much that it excites the cells to the point that they self-destruct, and that's called excitotoxicity. Glutamate is necessary for the flight or fight response, but it is also necessary for energy. We need to have glutamate. We just don't want to have too much for too long. Interestingly, testosterone, remember both men and women have testosterone, was shown to significantly increase the toxicity of glutamate, whereas estrogen, and men and women both have estrogen, significantly buffered against the toxicity of glutamate. So I thought that was kind of interesting that testosterone actually amps up the heat, if you will, and makes it even more neurotoxic, but estrogen does the opposite. And I guess you can kind of see that in people when you see how estrogen and testosterone seem to have opposing or balancing effects on the individual. So let's look at how glutamate interacts with everything. And I don't expect you to remember all of these interactions. That's why I made a little cheat sheet chart for you at the end. But recognizing that if glutamate is too high, which means that HPA axis is just, full bore and probably full bore for too long, serotonin's going to go down over time, which means the person may start feeling depressed, which means the person is going to have more difficulty sleeping, which means the person is going to eventually, when the endorphins wear off, feel more pain. Norepinephrine and acetylcholine go up when glutamate goes up. GABA goes down. Well, GABA is made from glutamate. So if glutamate is being used up as an excitatory neurotransmitter, then there's none left over to break down to make GABA. GABA is released when it's time to downregulate that HPA axis. So it makes sense. They're going to, be opposite ends of the balance. Endorphins are released when glutamate is released because your body is designed to not feel that pain during the initial fight or flee. If, as I said earlier, if that glutamate level stays too high for too long, you're going to start developing glucocorticoid resistance. You're going to start developing hypocortisolism. You're going to start developing endorphin resistance. So you're going to see the interactions that are supposed to happen during fight or flee stop happening. Whatever used to be secreted and trigger a response, eventually the body's just going to go, no, I don't have that in me. And it's not just a lack of response to cortisol. I want you to kind of bring that home with you, because a lack of response to endorphins, let's think about how that affects us. That means you're developing a tolerance and you need more of the endorphins in order to modulate your pain. Even your endogenous opioids, you can develop a sensitivity to. So chronic stress can actually lower, in the long term, can actually lower our pain tolerance if we start developing endorphin resistance. Dopamine is interesting. In response to glutamate, it can go up and it can go down depending on where we are in the brain. Dopamine is released and increases in certain areas of the brain during stress in order to help us with our energy. But mostly, the pleasure-promoting aspects of dopamine, the parts of dopamine that trigger the release of more endorphins, tend to not happen at that point in time because it's not time to experience pleasure. And dopamine is our I want to do that again neurochemical. And guess what? When you're fighting or fleeing, you don't want to do that crap again. You just want to get the heck out of there. So in large part, dopamine is going to go down under stress, but there are a couple little scenarios where it may go up. Not a big deal. What we really want to focus on is excitatory neurotransmitters tend to all go up together and suppress the inhibitory neurotransmitters. So stress tends to suppress and cause reductions in our calming neurochemicals. Endocannabinoids strive to keep glutamate activation within tolerable limits. So endocannabinoids are released when glutamate is released in order to try to keep it under control. It's a modulating neurotransmitter. It doesn't necessarily go way up or way down, but it tries to balance it out, kind of like trying to keep a warm bath. Cortisol and adrenaline go up with glutamate, that HPA axis. Thyroid reduces glutamate levels by stimulating reuptake. So interestingly, in the HPA axis, cortisol, adrenaline, glutamate, they're released, norepinephrine, it's released, and thyroid is also released at a certain point to help with metabolism and energy management, but it also stimulates the reuptake or the downregulation of the HPA axis by causing the reuptake of the glutamate. Testosterone can protect against glutamate-induced toxicity and oxidative stress in certain cases, and DHEA also provides some level of neuroprotection. Now remember, testosterone, estrogen, DHEA, progesterone all tend to go down with aging. And these chemicals, which are steroids, are helpful at reducing inflammation. So as people age, they may experience more inflammation and oxidative stress, not only in their body, but also in their brain, which means it's important to make sure that they are getting their blood tests done at their doctor and maintaining the levels of all of their hormones because inflammation is going to trigger that oxidative stress, which can trigger the variety of development of different diseases, as well as cognitive decline and depressed mood. So as those hormones go down, we're going to see side effects of that will present as behavioral issues. GABA is the main inhibitory neurotransmitter in adults, and it's created from glutamate, as I said. So when it's not time to be excited anymore, then glutamate gets broken down and GABA is secreted. Interestingly, GABA is considered the major excitatory neurotransmitter in many regions of the brain before the brain matures. So your anti-anxiety medications, the ones that act on GABA, may actually have an opposite reaction in young people. And that's important to just kind of recognize that they may be having a different reaction to things like Valium and Xanax that are acting on GABAergic receptors. Once the glutamate receptors develop, which is not until adulthood, then it switches around and glutamate becomes the major excitatory neurotransmitter. GABA assists in neurogeneration. That's awesome. So when you're young and your brain is forming, GABA is your main excitatory neurotransmitter, and it's also, stimulating the formation of neurons. Well, gosh, I want that. It also assists in reducing anxiety and fear, and is produced at relatively high levels in the insulin-producing beta cells of the pancreas. We know that people who have diabetes have difficulty with those beta cells, if those beta cells are even working at all. So people with diabetes may have difficulty with GABA levels, which can impact their mood in the long run. It suppresses inflammation and regulates muscle contraction. If people don't have enough GABA, not only may they feel anxious, but they also may have concurrent inflammation in the brain, as well as throughout their body. And we know that's associated with, drumroll please, depression and cognitive decline. GABA interactions. Well, as you would expect for your main calming neurotransmitter, it is going to increase serotonin, endorphins, dopamine, endocannabinoids, and progesterone. In general, it is going to decrease your stimulating neurotransmitters. Interestingly, though, GABA A receptors increase the release of norepinephrine, and GABA B receptors decrease norepinephrine. So that's one of those that can go either way, depending on which receptors are being stimulated. And norepinephrine actually modulates the synthesis of GABA. So if your norepinephrine's are out of whack, a lot of people who experience depression may respond to selective norepinephrine reuptake inhibitors. Well, guess what? When norepinephrine levels are balanced, then it's going to help balance GABA levels. GABA is going to, in general, react. Cortisol, adrenaline, thyroid hormones are going to tend to go down when GABA is released. Now, your endorphins are responsible for fear and emotional learning and are modulated by, or fear and emotional learning are modulated by your endogenous opioids. I thought that was interesting. So opioids, your natural opioids, not only control or affect pain, but they also affect fear and emotional learning. People who are abusing opioids, they're taking exogenous, outside opioids, they're throwing that opioid system into a tizzy, and so it's not reacting the same way. It's starting to become resistant to opioids, which very likely can be increasing anxiety. Endogenously, naturally released opioids directly regulate neuronal excitability. So if those receptors are not doing their job, if they are not able to regulate that neuronal excitability, you're going to see more fear and anxiety, which is one of the reasons we know people who use opioids often experience a significant anti-anxiety effect from them. And this is exactly why. The endorphins also modulate the HPA axis response. Chronic stress causes changes in specific components of the endogenous opioid system. Chronic stress is just really a bad bugger, including the mu opioid receptors. Now, there are lots of different opioid receptors, but the mu opioid receptors are the ones that are acted on by your endogenous opioids, but also the exogenous opioids, your methadone, your heroin, those things. So chronic stress will actually alter the functioning of that receptor. Immune cells have been shown to secrete endogenous opioid peptides, which bind to the peripheral opioid receptors to relieve inflammation and neuropathic pain. So when we do have pain, when we do have inflammation and the immune cells go there to try to repair the damage, they bring along with them their own painkillers. So think of it like the EMTs just showing up and they have painkiller that they administer before they stitch you back together. Another really interesting thing is that chronic overeating, and that means people who are regularly grazing, who are developing insulin resistance, who eat a lot, eat frequently, are almost always grazing on something. When we eat, even if we don't like what we're eating, when we're eating, it results in opioid release. That can lead to opioid resistance and promote overeating and obesity to regulate homeostasis. We're supposed to have a certain amount of our endogenous opioids or our endorphins in our body. So if we are chronically eating and those receptors are chronically getting bombarded with the opioids, then they may become resistant to them. So they're not working as well, which means they're requiring more to get the same job done. In order to do more to get the same job done, people can eat more. And then that increases the secretion of endogenous opioids. So feeding has been found to consistently trigger opioid release even in the absence of subjective pleasure. And that's important. So even if you're eating celery, it's actually going to trigger some opioid release in the brain. What do your endorphins interact with? And this is the same for exogenous opioids like heroin, just to a much bigger degree. But your endogenous opioids or your endorphins increase serotonin. In the peripheral nervous system, they increase GABA. In the central nervous system, they decrease GABA. They increase dopamine. Generally, when you have a pleasurable experience, you'll have the trifecta. You will have endorphins, dopamine, and serotonin released kind of all at the same time. Endocannabinoids both increase and decrease dopamine. It serves to regulate dopamine levels. In terms of your hormones, endorphins tend to reduce cortisol, reduce adrenaline, and suppress gonadal hormones. Thyroid, they're not really sure whether the endorphins act on it at all. That one is not highlighted because I couldn't find any research that looked at the interaction. In your endogenous opioids, actually also reduce testosterone. Interestingly enough, the one hormone in here that is increased is oxytocin. When we release endorphins, that's a pleasure chemical. Well, when we're feeling relaxed, when we're feeling happy, a lot of times that increases our desire to bond with others. And likewise, when we have a desire to bond with others, a lot of times endorphins are secreted when that happens, when we pet an animal, when we get a hug, those sorts of things. Dopamine is another one of our biggies, and it is responsible for motivation, executive functioning, mood, movement, and muscular activity, including, and it's implicated in things like erectile dysfunction, restless legs, and Parkinson's disease. We do want to know this. If somebody is on medication, for example, for erectile dysfunction or RLS, that is impacting their dopamine levels. Dopamine is big in regulation of energy and wakefulness. People with Parkinson's disease or on antipsychotics, both result in low levels of dopamine, end up feeling sleepy a lot of the time. They have a hard time waking up. So low dopamine, low energy. Low dopamine, low motivation. Learning, attention, and memory are also regulated in part by dopamine. It helps regulate insulin, the immune system, gastrointestinal motility. It actually serves to regulate the flow of information from other areas of the brain. Think of it like a conductor that helps regulate that. And it is made, as we talked about earlier, L-tyrosine produces dopamine, which is broken down to make adrenaline, noradrenaline, and actually thyroid hormones. Dopamine increases a lot of things. Interestingly, serotonin, norepinephrine, GABA, endorphins, and endocannabinoids, progesterone, and oxytocin. Not surprised that those things increase with dopamine. Those are our pleasure chemicals, pleasure hormones. Acetylcholine goes down, which makes sense. As serotonin goes up, acetylcholine usually goes down, so that makes sense. We talked about how with glutamate, dopamine may go up in order to help regulate energy response. But in general, dopamine goes down in the emotion processing areas of our brain under stress when glutamate is active. Cortisol, just like glutamate, is regulated in part by dopamine. So dopamine is out there to help with energy regulation. When the HPA axis takes off, a little bit of dopamine happens, but most of what we think about dopamine for happens in other areas of the brain, and that's suppressed during the fight or flee. Adrenaline and noradrenaline are made from dopamine. So as dopamine goes up, the body has the ability to make more adrenaline. Hypothyroid causes dopamine receptor sensitivity. When there's not enough thyroid, then there's not enough dopamine. So the receptors need to become more sensitive in order to grab on to any dopamine they can find. So it's important to recognize that, as thyroid goes down, it's likely that dopamine goes down, which affects the receptors. And as thyroid goes up, dopamine receptors don't have to be so sensitive because dopamine levels are adequate. Testosterone actually goes up in relation to dopamine. Oxytocin and progesterone also go up in relation to dopamine, but DHEA and estrogen go down. They have done some studies that they've found that people with schizophrenia often have low levels of DHEA and excessively high levels of dopamine. And when they regulated that balance, it helped with a lot of their symptoms, which I thought was kind of cool. And your endocannabinoids. I promise we're almost done with the list and we're going to start applying this in a minute. Your endocannabinoids maintain emotional, physiological, and cognitive, quote, stability. So they do a lot. They are responsible for, in part, appetite, digestion, metabolism, regulation of chronic pain and inflammation and other immune responses, mood and stress response, learning and memory, motor control, sleep, cardiovascular and reproductive function, bone remodeling and growth, and skin and nerve function. You should notice by now that dopamine, serotonin, your endocannabinoids, especially, and norepinephrine to a certain extent, all have very similar and overlapping jobs. So people who are having problems with sleep, it could be a dysfunction in their endocannabinoid system, not in their serotonin system, or not specifically with serotonin. In order to make sure that they have enough serotonin, the endocannabinoid system may need to be addressed, which is one of the reasons they found that CBD oil works for some people with depression to help relieve their symptoms, because the cause of their low serotonin was a dysfunctional endocannabinoid system. CB1 receptors are mostly found in the brain, and they impact GABA, glutamate, dopamine, and serotonin functioning. Cannabinoid 2 receptors, or CB2 receptors, are mostly found in the immune system. How do your endocannabinoids, these are the receptors that are going to be affected by marijuana as well as CBD oil, for example, as well as your natural endocannabinoids, your endogenous endocannabinoids. Well, those things reduce serotonin, often increase norepinephrine, acetylcholine, and glutamate. Interesting. They reduce GABA and endorphins and increase dopamine levels. So that's kind of interesting. We know that generally dopamine and serotonin kind of go up together, but the endocannabinoid modulates that interaction. We know that people with low dopamine may feel depressed. They are probably going to have low energy, difficulty concentrating, a lot of symptoms that look like depression. We know that people with low serotonin are going to have, apathy, more pain, difficulty sleeping, low energy levels. Same thing with norepinephrine. So when somebody comes in and says, I'm depressed, well, why? Exactly where is the system breaking down that is preventing the body factory from operating at 100% function and capacity? We don't really know. But it's important to consider everything that may be involved. Endocannabinoids reduce cortisol, adrenaline, thyroid, and testosterone. So those things are interesting. It reduces a lot of our stress hormones. Over here, but it increases some of our excitatory neurotransmitters. So it gives us energy, theoretically, without as much anxiety. Now, that is a gross oversimplification. And estrogen is increased. There was no research that I could find on DHEA, oxytocin, or progesterone interactions with the endocannabinoid system. We have just recently, maybe in the past 5 years, started focusing on the endocannabinoid system as a potential target for addressing mood and cognitive disorders. And cortisol, I know it's not a neurotransmitter, but it impacts so many things. I wanted to put it in here. Serotonin. GABA and dopamine are reduced when cortisol, your stress hormone, is released. Well, that makes sense. Endocannabinoids increase a little bit in order to help modulate the HPA axis, but they really serve more of a modulatory function. Norepinephrine, acetylcholine, glutamate, endorphins, adrenaline, and your thyroid hormone, if the system is working well, are all increased when cortisol is released. But if cortisol is released for too long, chronic stress, we start to see dysfunction in the receptors that respond to these excitatory neurochemicals. Testosterone and DHEA go down in response to stress. So people who have chronic stress may experience low energy, and maybe low libido, and have more difficulty dealing with stress. Remember, DHEA and testosterone are also steroids that can help reduce inflammation, and if they go down, then eventually inflammation is going to go up. Oxytocin, interestingly enough, not only does it increase in response to dopamine and the calming chemicals, but we also can see it increase in response to cortisol in certain situations, because oxytocin, we think of love, it being our bonding hormone, but it's also our love and protect hormone. So if somebody is in a situation where they feel like they've got to protect their children or their loved ones, oxytocin, even in a stress situation, may go up to promote that protective, pro-social behavior. Progesterone is the precursor to cortisol. Who knew? And is released in response to stress. Low progesterone can cause low cortisol. The interesting thing is progesterone balances out estrogen to help modulate mood. And so some people who have low levels of progesterone may have estrogen dominance, which can cause anxiety levels, even though low progesterone will mean that there's low cortisol. So the HPA axis is not going to function appropriately when progesterone is low. And estrogen, the HPG axis, the hypothalamic pituitary gonadal axis, is not going to function properly. So there are a lot of different ways or permutations that can lead to feelings of anxiety or depression. Now remember, after I finish the summary, we're going to go back to that infographic, so don't leave me quite yet. Neurotransmitters and hormones exist in a very delicate balance. Changing one often results in a cascade of other changes. Mood and cognitive symptoms may be caused by problems with a variety of different neurotransmitters or hormones. Aging naturally reduces certain hormones and consequently related neurotransmitters, which can lead to mood problems, increased pain, increased inflammation, and even increased immunity, or not increased, decreased immunity. So you can see, you think your grandparents, they have a lower immunity. Well, let's think about why. Your grandparents may tend to be a little bit more rigid about things or irritable. Well, there could be a reason for that. As people age, they naturally experience some cognitive decline. Well, let's think about why that is. And we'll look at that more in a moment. Differential diagnosis requires exploring the possibility of a deficit in a neurotransmitter or hormone due to insufficient raw materials to make it, so this process can't even begin. Deficiency in other chemicals that trigger its release. So if whatever chemical is going to trigger the release of serotonin is not available, or cortisol is not available, then it's not going to be released. Excess chemicals that degrade or trigger the reuptake, so it gets sucked out of the synapse too quickly. Or just plain problems in the neuronal signaling system. So whether it's the serotonin system or the GABA system, if there's problems in communicating those nerve impulses, then there's going to be potential problems. So let's take a look at that on the big screen. Let's just go with aging, for example. And let's look at what happens to these neurotransmitters when testosterone is low. When testosterone is low, how does that impact your endocannabinoids? Well, testosterone goes up in response to cortisol. It goes up in response to endocannabinoids, so that's interesting. But it goes down in relation to dopamine, and it goes up in relation to endorphins and GABA. So remember, purple is an opposite response. So if testosterone is out of balance, then you can see that, let's say an older person who has low testosterone, their serotonin levels may get too high, norepinephrine may get too high, GABA and endorphins may have difficulty. They may feel tired a lot of times, and their endocannabinoids may actually get too high. Well, what does that mean? That means that you're going to have differences or your changes in mood, changes in responsiveness. We know that as dopamine goes down, energy goes down. So if dopamine is low, if we think dopamine is low, or if somebody's on antipsychotic medications, then they're going to have lower levels of acetylcholine and lower levels of DHEA and lower levels of estrogen. So what are the impacts of that? When you have low DHEA, then you're going to have higher levels of calming chemicals, which when your energy is already low is not something that you want. So you can start looking and figure out, okay, if this person's serotonin is low, let's just say their serotonin is low, then their norepinephrine, acetylcholine, and glutamate may be too high. Their endocannabinoids and their cortisol may be too high. That could cause anxiety. Well, what does it mean? Then you go down here and say, well, if their norepinephrine is too high, how is that impacting everything else? Norepinephrine, as norepinephrine goes up, you're going to see acetylcholine maybe go down, so that can balance out. As norepinephrine goes up, you're also going to see glutamate go up. So you're increasing anxiety levels. And you can just follow it through that way, but it's interesting to note that things like testosterone level have such a dramatic impact on the different neurotransmitters. You know, low testosterone can cause a variety of problems, including depression, fatigue, lack of energy, that a lot of people experience. I know this is a lot of information to digest, but it's important for us to really recognize the importance of proper health behaviors, of our clients regularly getting their blood work done, because health behaviors, and we're going to talk about that tomorrow. It's a much lighter presentation tomorrow. We're going to talk about natural ways to provide your body the resources it needs to help balance your neurotransmitters. When you get things naturally, not by taking pills or something, not by taking supplements, but when you do things like get sunlight, how does that impact your system? Generally, our system is very self-regulating if it is not exposed to chronic stress, chronic toxins. It wants to survive. It wants to be healthy. So if we allow it, give it the resources it needs to, make the system function, and then we get out of its way, by reducing our stress, etc., then it is naturally, eventually going to largely rebalance itself. Now, there are occasions where there are problems in the signaling system. There are problems that are caused by genetics. That is true. And those people do respond well to certain medications, for example. But a lot of people, if they're patient, can rebalance a lot of their neurotransmitters. There's one study out there that indicates it's estimated that upwards of 80% of Americans have imbalanced neurotransmitter systems because of our chronic stress environment. Are there questions? Consider, if you're interested in this topic, consider sitting down with this chart and just following it and saying, okay, if somebody has low serotonin, then these things are going to be affected. All right, well, if they have low serotonin, that means they're going to have high norepinephrine. So what does that mean? If they have not high norepinephrine, how's that going to impact the system? If they have low serotonin, they're going to have high glutamate. How does high glutamate impact the system, and what symptoms might that cause? Looking and noting in general, the neurotransmitters that are excitatory and pleasure-producing versus the ones that are stress-induced, or excitatory and stress-induced versus the ones that are calming, relaxing, and pleasure-producing. If this podcast helps you help your clients or yourself, please support us by purchasing your CEUs at allceus.com or getting your agency to sponsor an episode. A direct link to the on-demand CEUs for this podcast is at allceus.com/podcast CEUs. That's allceus.com/podcast CEUs. To sponsor an episode of Counselor Toolbox and reach over 50,000 clinicians per week, go to allceus.com/sponsor. Thank you.